Alright guys, welcome to my channel. My name is Ashik and today we are going to talk about collision theory and later we're going to discuss about the Maxwell-Boltzmann distribution. Collision theory. Basically, the collision theory states that in order to particles to react, the particles must collide. Actually, let's use a different color for this. The particles must collide and also they must collide with correct orientation. Collide with correct and finally they must collide with correct orientation and sufficient energy. We'll talk about what this sufficient energy is in the next slide. All right, let's picture that this is the system and these are the particles. And these are the other reactant particles. So in a system, these particles will be moving around with some speeds, varying degrees of speeds. There are no particles that are stationary. Every particle will be vibrating or moving at some speed. And for a reaction to occur, these two particles should meet each other with the correct orientation and must have the sufficient energy, which is also called the energy of activation. Energy of activation. We'll talk about this more on the Maxwell-Boltzmann distribution. So why does correct orientation matter? Okay, so picture that this uh, this system has nitrogen monoxide. I wrote the nitrogen in green and the oxygen in yellow. So the nitrogen monoxide has green and yellow, and it reacts with ozone. All right, ozone has 3 O's. Now, and there's another a different case over here. All right. Now these two molecules meet each other like this, and let's say that this molecule meet like this. This case, the case one, the oxygen in the ozone hits the nitrogen atom, and this is the correct orientation in this scenario, and this will form. So this will form the required products. However, when these two collide with each other in this orientation, no reaction will occur. Because this is not the correct orientation. Suppose the said correct orientation in this case. Actually, the oxygen should have collided with the nitrogen, but it hasn't happened in this case. Okay, so the next part of the collision theory is about the sufficient energy, right? Energy of activation. So let's talk about that. These are two energy level diagrams, and in this case, the one in the right, we are going to draw an endothermic reaction. And in an endothermic reaction, the products have more energy than the reactants. So, how does the products have more energy? It absorbs it from the environment. So, if this is the enthalpy change, doesn't mean that if we give that, let's say this is the enthalpy change, and let's say that this is equal to 50 kilojoules per mole. Does it mean that if we provide the reactants with 50 kilojoules per mole, that it will turn into the products? No, because it requires a slightly bit more energy, and the curve looks like this. And the total height from here, the, the one I'm using the green arrow, is called the energy of activation, EA. A stands for activation and E stands for energy. Only if we provide this energy of activation, the reaction will proceed. Let's look at another case, and this is an exothermic reaction. Alright, in this exothermic reaction, the products have lower energy than the reactants. So the jump will be like this. However, initially it requires some energy, and this is shown by this green arrow again. This is the activation energy in this case. So if you think about it, petrol reacts with oxygen to produce carbon dioxide and water. However, if you keep the petrol in contact with the oxygen or the air, it doesn't mean that it suddenly blows up and it releases all the heat. No, you need that initial spark. For example, in the vehicle's engine, the spark plug provides the energy for the reaction to take place, and that is what this activation energy means. And if you observe in both of these circumstances, the activation energy goes from the energy level of the reactants to the peak of the change. It doesn't grow from the products, it goes from the reactants. All right, so now we know that what collision theory states. Let's look at about what Maxwell-Boltzmann distribution is. What is the Maxwell-Boltzmann distribution curve? And before we see what this is about, I need to say that there is something else called the Boltzmann distribution. Boltzmann distribution. This is not what Maxwell-Boltzmann distribution is. This is not Maxwell-Boltzmann distribution curve. This is something different. So you'll hear about that. You'll hear about that in other places. So please be aware of it. So again, what does Maxwell-Boltzmann distribution curve shows? It shows the distribution of kinetic energy of particles in a gas at constant temperature. This is what the Maxwell-Boltzmann distribution curve shows, and it looks like this. This is what it looks like, and in this axis, in the x-axis, it shows the energy, and in the y-axis, it shows the number of particles. All right. So basically, what it shows is a picture of all the energy distribution that the particles in a gaseous system has. For example, if you take a sample of gas, not all the particles or the molecules will have the same energy or the same kinetic energy. Every one of them have different kinetic energies, not the same at all. Some may have very large uh, some may have very large kinetic energies, and some others may have very little. So this is what Maxwell-Boltzmann came up with, and your exam board might ask you to draw this in the exam. So when drawing that, there are some key points that you may have to remember. And number one is that the curve starts from the origin, from here. It doesn't go from up there. It goes from here, 0, 0 coordinates, and it never touches the x-axis again. Here it doesn't touch, it doesn't go down like this. This is wrong. It shouldn't touch the x-axis. And another thing to remember is that the area under this curve, the whole area under this curve, represents the number of particles in the system. This is what your exam board and the test expects you to know. However, it is worth noting that this is not perfect at all. For example, the fact that the curve never touches the x-axis again cannot be very true, because if the area under the curve is equal to the number of particles in a closed system, there should be a finite number of particles, and if the curve never ever touches the x-axis again, the area is equal to infinity. So it is not the best representation of the distribution. Also, the fact that this doesn't continue is also wrong. If you take a system and measure the kinetic energy of the particles, there will be some end. But we don't show that because some particles may have very large amount of energy when compared to others. That is what the exam board expects us to know about the Maxwell-Boltzmann distribution. And another thing is that you may be expected to know the variations or the effects on this graph due to various reasons. And that is temperature and catalyst, the effect on this graph due to the temperature and catalyst. And we'll talk about that in the next video, and I'll make a playlist for this whole kinetics section. And till then, thanks for watching. Please do subscribe to my channel and hit the like button if you like this, and please do comment down below of anything that you want me to cover. Bye bye.